I'd like to take some time to discuss other possible substrates besides just the alkyl halides that we've been focusing on for the past few videos. Tosylates are another class of leaving group, and they look like this. Where this whole piece here on the right side of that dashed line is called the tosylate. And you could think of that as just a very large chloride or a very large iodide. If we take a nucleophile and let's use OH minus here as our nucleophile. The mechanism is identical to the Sn2 style mechanism that we've discussed previously. The product is just what you would expect, a primary alcohol. And the leaving group in this case you should be able to draw as well without too much trouble. And you should also be able to tell me why this leaving group is very stable. Why do you think this is such a stable leaving group? In fact, it's one of the best leaving groups we will encounter this semester. Well, I hope you've come up with a reason that deals with the delocalization of this negative charge here. We could draw a couple other resonance structures. There I've given you a starting point with those red arrows. We can show that that negative charge does not reside simply on that leftmost oxygen, but it's shared equally among all three of the oxygens as part of this sulfonate functional group. So this is a very stable leaving group. And you can read about some others very similar to this tosylate in our text. I don't feel the need to spend video time on that. So let's look at how we might create a tosylate. Let's look at this chiral alcohol, and we can use tosylchloride, which is going to look very similar to the tosylate leaving group I just drew. So we abbreviate this tosylchloride, so I can write that here. We often use pyridine as a sacrificial base in this situation. Sacrificial base simply means if there's any acid produced during the reaction, we use this base to soak it up. And oftentimes we will abbreviate pyridine PY or PYR. And so the mechanism of this step is a little bit beyond the scope of the first semester. It will be the topic of second semester topics. But we can draw the product, and I'm going to write OTS here to save room. But basically the OTS is the same as this piece that's on the the right side of the dashed line. So, and you'll also notice that the chirality center here remains in the same configuration when we've turned our alcohol into a tosylate. So we are not changing anything about the chirality center yet. Now though, we've got a good leaving group, and let's say I wanted to use NaSH as my nucleophile. We know to expect an Sn2 style reaction, and we will get inversion in this case, and we'll get OTS as the leaving group. I'd also like to point out that right here I get pyridinium chloride as my byproduct because I've created an H and a Cl as a byproduct from this tosylation process. The pyridine there is there to soak up the HCl, because otherwise there might be something on this side of the molecule that is sensitive to acid, and I don't want it to experience the acidic environment I've created by making this tosylate. So we use the sacrificial base to soak up the HCl. This we can just wash away or separate out, and the strong acid does not interfere with the rest of our reaction. So that's how we would use a tosylate. We can now make a tosylate from an alcohol and tosylchloride. We can use the tosylate as an excellent leaving group. Let's look at another alternative substrate now in the form of alcohol. So we can look at a generic alcohol here, maybe propanol, and we know that this is a poor leaving group. Why is it a poor leaving group? Well, let's look at what happens if it leaves. And I'm going to just make this tertiary here so we can have perhaps the possibility of it leaving. but we've made a very strong, very reactive leaving group now. The OH minus, we know it's a strong base. It's not a very good leaving group at all. And so there's other things we'll do to make the alcohol reactive in sort of a substitution or elimination process. One of those is to react the alcohol with HBr. And the resulting product is simply substituting a Br for the OH. Meanwhile, we make H2O as a byproduct. This is an Sn2 process. How would we look at that? First thing that's going to happen is we're going to protonate the OH. Now you can see that we have water here sitting on our primary carbon. We've also created a bromide by removing the H from HBr. That bromide can attack the primary attack the primary carbon, kicking off water and leading to our primary bromide. Another option is if we have maybe a tertiary alcohol. We can react that with HBr as well. Protonate the alcohol. And now, before the bromine can attack, remember this tertiary carbon right here is very hindered. We can remove the leaving group. Losing water. And now the bromine nucleophile can attack, bringing us to the expected product, plus H2O as the byproduct. We can also use concentrated sulfuric acid to react with alcohols. Let's look at this tertiary example. Now, concentrated sulfuric acid typically means as strong of an acid as we can get with the minimum amount of water mixed with this strong acid. So there's not going to be many reagents other than H2SO4. The book does mention that we probably have H3O plus as our reactive acidic portion, so we might use that as our source of H plus ions. So what we can do here is redraw H3O plus so we have a better place to start our mechanism. We'll protonate the alcohol just like we did with HBr. And here I lost a little bit of water. This is a tertiary alcohol, so we're going to, actually I'm going to draw it this way. I'm going to lose water. And now remember that we are in concentrated sulfuric acid, so there really isn't a lot of water present. I've just made one water, maybe there's another water around, but by and large there's not a lot of nucleophiles around here. And so what's most likely going to happen is that we will lose a beta hydrogen to form an alkene. So I can use water as my weak base. The beta hydrogen gets lost, those electrons drop down to form a pi bond, quenching the cation, and I've just produced an elimination reaction. So this would be an E1, also dehydration. So this is an E1 mechanism. It is a dehydration because we've lost water in this step right here. And of course, because I formed the cation, I'm going to form any possible alkene product that I could possibly form, including the less substituted kind. So the major product, of course, is the most substituted alkene, but I am going to form some minor product as well, and it's possible there's more than one of those. In this case, there was only one. We could also show this with a secondary or a primary alcohol, and in this case, we would protonate the alcohol, but it would not just leave, because that would leave us with a primary cation. So most likely, another bit of water present in the acid would steal the hydrogen, at the same time pushing off the leaving group, giving us sort of an E2 process in this case, simply because of the identity of the substrate. And that would give us this alkene, this terminal alkene.